In this video we're going to look at covalent bonding, which involves the sharing of a pair of electrons, usually between two non-metal atoms, but sometimes between a metal atom and a non-metal atom. That will depend on the electronegativity of the metal, and for more on electronegativity you can see the electronegativity video further down the page on the website. Before I start drawing out electron shell diagrams, we're going to talk about a rule called the octet rule. So the octet rule states that there is a tendency for an atom to adopt a noble gas configuration when bonding, due to the stability of this configuration. That just means either 2 or 8 electrons on its outer shell. Now there are exceptions for this, to this rule. For example, boron and aluminium, when it bonds covalently, will not form 8 electrons on its outer shell. And something further across the period in the periodic table, like sulfur or chlorine, they can have more than 8 electrons on its outer shell. But this is just a general rule that atoms tend to obey. So we're going to look at the simplest of elements, and we know that hydrogen, with its 1 electron at the outer shell, actually exists as a diatomic molecule. What does this mean? It means that there's 2 hydrogen atoms in every molecule. So if I draw another hydrogen beside it, that exists like that. And the electrons themselves are shared between the 2 hydrogen atoms. I'm now going to redraw that with the 2 electrons inside in a shared orbital between the 2 hydrogen atoms, because a covalent bond itself is the strong attraction between the bonding pair of electrons here and the nuclei of both atoms. Okay, so the nuclei of both hydrogen atoms are strongly attracted to the shared pair of electrons. That's what makes up the bond itself. So I've just redrawn my covalent bond with the electrons shared between the 2 hydrogen atoms. The reason for this is because the electrons themselves can't be pinpointed at any point in time, so it really is just a cloud of electron density. That's the way we can think about it. That fluctuates or moves between the 2 hydrogen atoms. For more on that movement, you can see the intermolecular forces video. And the last representation for that would just be what's known as a stick diagram, where I just have the 2 hydrogens separated by a bond, and that bond itself is the covalent bond. That is also the covalent bond, which is just the shared pair of electrons, and I could do the same here for those shared pair of electrons. That's what the covalent bond is, a shared pair of electrons. We'll now see what happens when carbon bonds to hydrogen. So I know that carbon is in group 4 or 14 of the periodic table. If it's got 4 electrons on the outer shell and it's going to form covalent bonds, which is what carbon does, then it will form 4 covalent bonds, which we will depict now. So CH4, and I'm just going to draw the orbital overlap diagram, which is the shell overlap diagram here, will look like this. It will have a central carbon atom, and then it will have 4 separate hydrogen atoms surrounding it. Each hydrogen atom has 1 electron as outer shell, so contributes 1 electron to the covalent bond, and each carbon atom on its outer shell only, I'm not going to draw the inner shells, the carbon atom has 4 electrons in its outer shell. So what we see here is that each one of these overlaps is a covalent bond, so there are 4 covalent bonds around the carbon atom. So that will look something like this. Now, that's a simplified diagram. I'm not taking into account the shape of the molecule at all, but carbon itself has 4 covalent bonds and 8 electrons on its outer shell when bonded. Next, we're going to have a look at another molecule. We're going to look at what happens when nitrogen bonds. When nitrogen has 5 electrons on its outer shell, it's not going to form 5 bonds because that would give it an outer shell configuration of 10 electrons. what it does is it just forms 3 covalent bonds. So we're going to draw a central nitrogen atom with 3 hydrogen atoms around it and look and see what happens. Now we know the hydrogen itself contributes its 1 electron, and nitrogen will contribute, well, has 5 electrons in the outer shell, so there'll be 1 there, 1 there, 1 there. Okay, that's 3, and 2 other electrons. Now those 2 electrons just sit on top of the nitrogen atom like that. More specifically, those electrons fill an orbital surrounding the nitrogen atom, but this is called a lone pair of electrons. And each of these 3 is known as a bonding pair, which is also a covalent bond. Just to draw it out, this is how we will depict it without drawing any 3-dimensional arrangement, like that, with the lone pair just sitting on top of the nitrogen like that. The last one we'll look at is just water. So we'll look at oxygen. Oxygen has 6 electrons on its outer shell. Again, it's not going to form 6 covalent bonds because that will give it a total of 12 electrons on its outer shell. What it does is it just forms 2 bonds. We know that this is water. So if I draw the oxygen here, we know that there's 2 hydrogen atoms, each contributing 1 electron. And the oxygen contributes 1 electron to each bond, but it also has 4 remaining electrons because we know that oxygen has 6 on its outer shell because it's in group 6 or 16. 1, 2, 3, 4, 5, 6. And now it's got a total of 8 electrons on its outer shell, which is a noble gas configuration. And hydrogen has a total of 2 electrons on its outer shell, which is also a noble gas configuration. So another way of depicting water is like this. So when thinking about how many bonds something might form, the easiest way to think about it is probably that unpaired electrons on a central atom will just pair up. And the maximum number of electrons that can pair up is equal to the number of electrons in the outer shell of that element. The last thing we're going to discuss here is what's known as a dative covalent bond or coordinate bonding. And this is where one of the atoms will supply both of the electrons in the bond. So if one atom is supplying both electrons, then those electrons are probably coming from a lone pair. Transition metals quite often form dative covalent bonds because they have empty orbitals, which another element is able to fill with its electrons. But we're not going to go into that detail now. We're going to talk about a very straightforward one that is very important for chemistry later on, and making connections with the acids topic as well, especially. So it deals with water and hydrogen ions. Well, a hydrogen ion is just H+. Okay, it's when the hydrogen atom has lost its electron. So essentially it's just a proton. What happens when this hydrogen ion comes in contact with a water molecule? Well, the lone pair of electrons here form a bond with this hydrogen. So this arrow just depicts that the electrons are going to form an interaction with this hydrogen ion, and I'm going to depict it now in a diagram. Now the reason I've drawn square brackets around this is because we started off with a hydrogen ion which is a plus charge, and we end up with another ion. That's called a hydronium ion or hydroxonium ion. It's actually really important in the theory of acids. The reason it's important because all acids are substances that actually release H+ ions, but H+ ions don't actually exist in solution because there's too much charge density on such a small species like this that whenever water is around, they form this interaction here where you've got an oxygen surrounded by 3 hydrogen atoms. As a result of oxygen's electron density being drawn away to form a new bond, it's got a positive charge, and that is H3O+, which we will meet later. A dot and cross diagram of that will simply look like this. We have central oxygen surrounded by 3 hydrogens, those 2 hydrogens have donated their electrons,
to the bond, and this oxygen has it's a pair of electrons like that, but both of these electrons have actually come from the oxygen. As a result of that, because this was a hydrogen ion to begin with, the species is positively charged. And that hydronium ion is actually the source of all acids.